Welcome back. For our next video, we're taking a look at difference of squares, sums of squares as prime, and perfect square trinomials. The difference of squares is by far the most important quadratic because it comes from two terms, and that's plus and minus. We're going to make use of this fact that there is no middle term. This is like one of the ninja math secrets. If I have like an a plus b, and one of those has a radical, a square root, then I multiply it by what's called the conjugate. That's what these are called, conjugates. Then the result is a squared minus b squared. So wherever that square root was, now it's a squared. It's not a square root anymore. Likewise, when we have complex numbers, if I multiply a complex number by its conjugate, which is the same front thing, the same back thing, I just change the plus to a minus or the minus in the middle to a plus, and multiply by that, I have a squared and a squared. The complex part, the I, when it's squared, becomes real. And again, you don't have to know about i's right now. I'm just kind of trying to foreshadow why this thing is so very important. But in any problem where we ask you to factor, like some of those really ugly fraction equations that you guys are probably seeing in your homework now, these show up very, very often, especially the ones where you have to factor. A lot of times one of them will be a difference of squares. Now, sometimes you can get so overexcited by difference of squares, you start thinking the sum of squares will factor. It does not. When we get to complex conjugates, it will. But it doesn't factor into real numbers. And then we have the perfect squares. So if I have a plus b squared or a minus b squared, I get a squared plus 2ab plus b squared. So what the book wants you to do here is look for this particular pattern in quadratics. Seeing that pattern can actually be more difficult than you realize. I like to think of it as this is a potential chance. So if you're starting the problem and you notice one of your numbers is a perfect square, kind of like pause. Is this a perfect square? Is it just going to be the same numbers? And you can kind of make an educated guess at the answer, check it out, done. Assuming you're right. If you're not right, then rewind, just go back and do the AC method and it works. These will all work with the AC method. It's just you can save yourself a little bit of time if you happen to notice it's a perfect square. But memorizing that, you guys have better things to memorize. Also, I'm not big on memorization because you guys will have Google from here till the end of the internet. All right, so a squared minus 16a plus 64. 64. I know that number, that's 8 squared. And 8 makes 16. This is a perfect square. So what I literally do is it looks like guess and check, and I apologize for that, but it is a guess. 64 is 8 times 8. It is a negative 16. So minus and minus, and then you just double check. Minus 8a would be minus 16a. Negative 8 times negative 8 would be positive 64. A and a would be a squared. It works. But we can be even lazier and write it like so. Now remember, when we talked about multiplying these, I had you guys focus on how the constant term and the coefficient on the middle term interacted. So if you notice the last one is a square, figure out what number squared it is, double that number and see if that's your number in the middle. If so, there's that number that squares. Now sometimes it can look a little crazier, like 13 over here. So 9x squared plus 30x plus 25. AC method will totally work here, but 9 times 25, but if you notice 9 and 25 are both perfect squares. Oh, let's try. Let's make the leap of faith. So 9x squared would be 3x and 3x. 25 is 5 and 5. 30 is positive. So all we got to do is check. That is 15x. That is 15x. Those combine to 30x. 9x squared, 25. There is our answer. 3x plus 5 squared. Because we can be lazy. I think Alex may actually force you to write it as a thing squared, but sometimes the directions also give it away that it's going to be a perfect square. So that's why it pays to read the directions. All right. So we will make use of this pattern, but it will be in a slightly different way. And it does come up in pre-cal, so if you're going to continue on, at least be familiar with this. Now this one, now 52, negative 20. What? Oh, it's not even in order. Okay, step 1. Fix the order. Now, after a while, like if you do a lot of these for practice, and then you get to one where they swap the order, like sometimes you are just so in the zone, you don't even notice. So I don't want you guys to miss points for something silly like this. Because remember, I don't write the Alex problems. I will help you solve them, but I don't get to write them. So this doesn't look like a perfect square, but they're all even. So let's pull that 2 out. So now it's d squared minus 10d plus 25. There we go. There's my square. That's 5 squared, and double 5s is 10. We just need to account for the minus. So if you're feeling really frisky, you could actually jump straight to the squared. And we are actually going to see this process pop up when we start looking at graphing parabolas, graphing these quadratics. So be on the lookout for this kind of patterning to show up. We'll have some formulas hopefully to help us out, but I'll have to see how our co-teacher wants to handle formulas. All right. Then our last one here, a 9 and an invisible 1. 1 is a perfect square and a perfect cube and a perfect fourth. It's perfect everything. Yay, 1. 9 is indeed a perfect square. We have x's and y's. Well, that's fine. We're just going to see x's and y's everywhere. So 3x, 3x, y, y. That 6xy is indeed positive. And just to check, y times 3x, invisible 1 times 3 would be 3, y and x, or x and y, because we usually write them in alphabetical order. And then our outers, 3xy. Those are indeed like terms that add back up to 6xy. So poof, jumped to the answer. 3x plus y squared. Whoa. And the crowd goes, no, the crowd is asleep. Competitive math puts you to sleep. All right, next up is the difference of squares. So the first two were written a little weirdly, deliberately. They may or may not show up like this in Alex, but I figured it looks interesting at least. And then I have a double one down here with the x to the 4th minus 16 that I'm adding in. All right, so these guys here, I have ugly squared minus 81. 81 is a square, ugly is a square. So this is a squared minus b squared. What's missing is the middle term for this to look like an actual quadratic. So the missing middle term up here is a 0. A squared plus 0ab minus b squared. So when I'm thinking back to finding my perfect pair, I need a perfect pair that adds to 0. The only way to get numbers that add to 0 are if they're additive inverses or opposites. So like +4 and -4, +3 and -3, plus 2.5 and minus 2.5. Doesn't actually really matter what the number is as long as one's positive and one's negative. So the product would be that number squared, but negative. So that's why we have minus b squared and why it must be a minus, because I need opposite signs to add to that 0 in the middle. So once we have those opposite signs, then our factoring is a plus b and a minus b. So if you're using this like a formula, you just have to figure out what the a is and what the b is. So here I have ugly squared minus 81. Well, I know 81 is 9 squared. And my ugly here is the placeholder for a. So I'm going to use it like that. So that is 3z plus 1 squared minus 9 squared. So now you can see the b here is 9. So I'll go ahead and use extra parentheses because safe math is the way to go. When in doubt, wrap it up. But this one will be minus 9. Now seeing those parentheses like that can be really confusing. So I'm going to go back in and change their color. Oops, got rid of a 3 on accident. All right, that's a little bit nicer to see. Now the inside here, so the parentheses I took all the effort to put back in, are they actually doing anything? They are not. So it's useful to kind of show the a plus b, the a minus b, but we don't actually need those yellow parentheses. So this is really just 3z plus 1 plus 9. Hey, like terms, I can put the numbers together. So we would get 3z plus 10. And then over here, still a 3z, but 1 minus 9 would be minus 8. So there is our factored form because they happen to give us a difference of squares. Now we could have taken 3z plus 1, multiplied 3z plus 1, worked it all out, minus 81, worked through all of that craziness, and we would have ended up in the same spot. So noticing it's a difference of squares or being told to note it's a difference of squares, because the directions really do tell us, can save you some work. So this is, to me, this is kind of pushing you guys to think outside the box for the way these things can work. And likewise, the A doesn't have to be the crazy ugly. B can be the ugly. So 25 is 5 squared minus, there's our ugly squared. So again, same thing. We're going to see 5 and 5. We're going to see a plus and a minus. We're going to see an x minus 3 and an x minus 3. So before, parentheses were not necessary. Write them anyway. Better to be sure, because look here, it matters. This second binomial with that minus sign onto the part with the parentheses, if you didn't write the parentheses because you're like, hey, we don't need them, you'd just write minus x minus 3, and then it would be like, uh-oh. We'd have a slight boo-boo. All right. So the parentheses on the first one aren't doing anything, but I am just going to write it without the parentheses, and then in a minute we'll keep going with that. Over here, though, we need to distribute this as a minus 1. So we are going to see a minus x, but I need to see a plus 3. Then on this one, 5 minus 3 is 2. I'm going to go ahead and keep the order 2 plus x, but you could write x plus 2 if you want, that's fine. Then over here, it is 5 plus 3 is 8 and minus x. So I knew we were going to have the minus x on the second one, so I kept the x in the same position, just that's the way I like my math. It really doesn't matter though. You could even swap the second one, but you would have to write it negative x plus 8. With the parentheses including the negative inside the parentheses, not outside it. So that's why I just, if we have a negative x from the way it worked out, then I tend to put it second. This is also why I factor the negative when it's on the a. Now our start of the problem, it didn't look like it was a negative x squared, but that minus sign would distribute after we would multiply out the x minus 3. But that is our end result. Alrighty. Now x to the 4th minus 16 will come up again, I promise. Because anytime when we start talking about graphing things bigger than parabolas, we almost always pull out one of these guys because the numbers are small, it's easy to factor, and you can see where the numbers show up in the graph. Sometimes they might even throw in like an extra x or x squared multiplied to all the terms. But let's talk about how to factor that. So I have x to the 4th minus 16. And you might be looking at this, well, you know, I know there's a difference of cubes. Is there a difference of fourths? Sort of. It's just a double difference of squares. So x to the 4th is the same as x squared squared. And 16 is the same as 4 squared. So now I can see my a is x squared, my b is 4. So that is what we are going to see in our factored form. X squared plus 4, x squared minus 4. All right, so I've done my difference of squares. This is not done. But be careful. This one does not factor anymore with real coefficients. Now, when we get to talking about these later, though, that will produce complex roots. And we will have a way to like use the complex roots and work our way back to something that looks like x to the 4th minus 16. So just trying to preview some of the craziness, where we're going, why we do the madness that we do. No, I take that back. I really don't have a good why. So 4 is 2 squared. So we have another difference of squares. We would get x plus 2 and x minus 2. So I end up with 3 things being multiplied. Now the order you write those down in does not matter. Alex should take it any which way. If it doesn't, please email me and I will go argue with it. But this kind of thing is like one of the favorite test type questions because you have to be paying attention and think, but it's not overly complicated. It's just making you do it twice. It's also an easy way for us to give you partial credit for doing part of the problem. But I am telling you, it is a test favorite. So that way, when it shows up, you know about it. Hint, hint, nudge, nudge, wink, wink. If you're not sure what I'm doing with the winking, come see me in office hours. I'll explain. And then, since some of you guys were actually using this on the quiz, props, like that actually totally works. The multiplication for the class that had this, because one of y'all didn't, I actually gave you the result of factoring cubes, and you had to multiply, and you ended up with x cubed plus 8. All right. So this is a thing math teachers sometimes make you memorize. So I'm going to talk about it from that perspective. Honestly, doesn't show up that often because we don't like it. So one of the ways I've taught this is this acronym, SOPPS, and it kind of forms a nice rhythm. So some people will say square or same, but this is to remember the pattern at the end of that. So the first part is the same, like we have a cubed and b cubed, so we get a and b, and it's the same sign. So like this x cubed plus 1, we're going to see x plus 1 is the first one. Then we have the squared term, the opposite, the pair, and notice there's no 2 here. The 2 was in the perfect square trinomial earlier. Here there is no 2, it's just the pair. Always a plus here because it is b squared. So whatever b is squared should be positive. Now, this crazy mess here, the second one, never factors with integers. It can be solved with the quadratic equation, and it gives you ugly numbers. Most of the time, it gives you ugly imaginary numbers. In fact, I think that might actually be all the time because these graphs are kind of boring. Yeah. Alrighty. So we're just going to make use of this pattern to factor these. And the only other way to really produce this would be to use long division, which we are going to get to, but it'll be a bit. So mostly I'm just covering this in case it shows up in your work. But I'm not going to 100% commit, but I'm probably not going to put it on the midterm. All right, so x cubed plus 1. So our a is x, our b is 1, because 1 cubed is 1. So, and we get a plus, so one of the ways you can do it is you can go through and like jot in all the signs, just boom right away. Then this is going to be an x, this will be an x squared, this will have an x, and then our b is 1, 1, 1. Oh, that does not look like 1. 1 squared technically, but that is 1. So what we would type would look like this. And when you have a sum or a difference of cubes, they both factor. Do not try to factor that quadratic. It never goes anywhere. So I'm just telling you that to kind of save you the annoyance. Alrighty. Now, sometimes it looks like this ugly mess. So 16, that wasn't a cube. We just did that. That was a fourth. But 54 is even. So this has a common factor. This is one of those math teachers and math textbooks really love this stuff. So we pull that 2 out, and now 27, x to the third minus 8. So when you do a lot of these, you start getting familiar with your cube numbers, but you could also just like real quick on the calculator, cube a bunch of numbers and just write them down just so you've seen it. But 8 is 2 cubed, 27 is 3 cubed. So for this one, I'm actually going to write the kind of intermediary step. So 27x cubed is really 3x whole thing cubed. Minus 8 is the same as 2 cubed. So there is our a, there is our b. A is 3x, b is 2, and we're going to see an annoying 2 out front. So there's our 2 out front. We have a minus, so it will be a minus here, opposite sign here, always a plus. Now that 3x here, safe math. This is 3x squared, parentheses are important, and a 3x here for my pair. This will be 2. This will have a 2. Save math. There. Even if you don't write the parentheses, I want you guys to think with the parentheses there. Anytime you're using a formula like this and you are substituting one thing for another, use the parentheses at the very least in your mind, or write them out if you're not as comfortable thinking with them yet. All right, and now we are just going to clean this up because that is a mess. So 2. So the parentheses in the first one weren't necessary, but better safe than sorry. We're going to go with sorry, not pregnant. Sorry. 3x squared, 3x times 3x would be 9x squared plus 3 times 2 is 6x, and 2 squared is 4. I know this looks very pretty. You're like, there's a 9, there's a 4. It always looks like that. That middle number will not have a perfect pair. It never, ever factors. You can prove it. I'm not saying to prove it. It's kind of annoying, but it can be done. So there's our factored form on that one. And then we have the last one where I think to myself, why did I do that? So remember what I did with the x to the 4th and the 16? I did that here. I should not have done it here. I am sorry. But just in case, we'll go through it. Feel free to skip this one though. This is more of a like, hey, just in case. But this is a sum of cubes, so x to the 6th is really x squared to the 3rd. And then 64 is 4 to the 3rd. It is also 2 to the 6th. So this is actually a sum of 6th powers. There is the possibility we'll see something like this when we're going to graph some of the crazier polynomials, or when we're looking at our weird roots. This can show up. But it's weird because it actually doesn't have any real roots. It's a whole bunch of imaginary ones. But it can be factored slightly. So, same, opposite, always positive. X squared here. X squared squared. And an x squared. 4, 4, and 4 squared. Now you do not have to write it this way or think through it this way. I'm just trying to verbalize and show you guys like how I use these kind of formulas. Although I am doing it from memory instead of like pointing at the formula, but you guys don't see my pointing well. All right, so x squared plus 4. So if I was really feeling devious, that would have been minus 64. This is now x to the 4th minus 4x squared plus 16. And remember, if this factored, square root of 16 is 4, double 4 is 8. We don't have the double. This will not factor as a perfect square. That's it. If this had been minus 64, this would have been x squared minus 4, which would factor as a difference of squares. So that's kind of like the Frankenstein factoring math, cubes and squares together problem. And it's generally only 64 or 1, because 3 to the 6th is ugly. And for this silly trick to work, it does have to be a 6th power. All right. So that is all of the crazy factoring I have for you. Again, come to office hours, ask me questions. See you later.